Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In today's tutorial, let's talk about Gaussian mixture model and apply it to segment images. When it comes to machine learning, you can typically generalize the approaches into two different umbrellas. One is unsupervised and the other one is supervised. A good example would be if you have an image and let's say you have four different kind of phases or regions that you're trying to segment. One way of segmenting them is just telling the software that okay, we have four different features, go ahead and figure out where they are. This is unsupervised segmentation, and supervised is where you can actually supply a labeled image where you kind of, let's say, paint the pixels and then label them and then say, okay, here are the regions that I am saying that this is my ground truth, and use this, train the algorithm, and in future for other images, use that trained model to segment future images. So that's as you can imagine, that's a supervised segmentation. So in the last tutorial, we talked about k-means clustering, for example. That's a good example for unsupervised segmentation because we have a bunch of data. In our case, because we are focused on image segmentation or image processing, our data is nothing but pixels in our image. Of course, this can be used for any data, right? So the k-means is a good example of unsupervised segmentation. And Gaussian mixture model is also a clustering technique, just like k-means, with a slight variation actually. And I'm going to explain what that variation is. But Gaussian mixture model is also another example of clustering technique, which is again that falls under unsupervised uh, image segmentation or data segmentation or data processing. So before writing any code, let's understand what Gaussian mixture model does, and I will stay away from using any equations. Okay, for those of you biologists or even material scientists who are not comfortable with equations. If you really want more information, obviously go ahead and Google search, or even on YouTube, there are excellent videos that go in depth about Gaussian mixture model. So first of all, let's look at, let's say we have some data, okay? Maybe it's nothing, oh, sorry. Maybe it is just a bunch of pixels with some pixel values, but we have let's say, some data points. This can be, again, like I said, pixels. Now, we want to divide this into two different clusters, for example. When we use k-means, we started off by saying, okay, I want to assign randomly two cluster centers. First of all, we're defining that my n equals to 2 in this example. And then let's say, okay, I have cluster 1 or center 1 and I have center 2. And then from each and every data point, it looks at the distance from that data point to C1 and also from that data point to C2. Because this one is closer to C1 and that one is closer to C2, this will be assigned or this will be allocated to a cluster that's centered around C1. Yeah, this will belong to C1. This will belong to C1. That one, depending on the distance, even if it is slightly closer to C2, that will become C2. That's it. It's a binary. It's either C1 or C2. That's pretty much it. So once we assign those, then once we assign them into C1 and C2, the next iteration, it calculates the mean of all of these values and then moves the C1 to that position, wherever that mean is. Okay, I explained this in our k-means, so I'm not gonna again fully explain this, go into details, although looks like I have. Now, what if that's the k-means, by the way? Okay, so which is fine, but what if some of your, in fact, maybe to make a point, let's change the color. My data points here, apparently I'm bad at changing the colors. Let me do that. Okay, so I have a data point here, and all of these belong to cluster number 1. And I have another cluster where I have the values, blue right here, and then I have some of these blue pixels right here. Okay, so what I'm trying to say here is k-means has some limitations because it's a hard assignment of either C1 or C2 in this example. But what if clusters overlap, for example? How do we deal with some of these? So apparently it looks like Gaussian mixture model works very well in these type of scenarios. So what is Gaussian mixture model? Now let's let me actually go ahead and clear the board here so we can start from scratch. So let me do that. Okay, so now if you look at image histogram, okay, so let me draw a dummy histogram for now, okay, blue color is okay. So if you look at any image histogram, so if you have something like this, okay, so what do you say? How many regions do you have? Maybe there is one, two, three, and four different regions in your image, right? I mean, if you may have an image, uh, again, I apologize for bad drawing, and then you may have like one region with certain gray level, another region with a different gray level, another region with a different gray level, and so on. Okay, so if you have these, then and they are not very well separable. If these four regions are very well separable, then you are lucky. It's use just histogram. Do not do anything fancy. If you have an image that has a histogram like this, okay, that has a histogram like that, then just put a hard limit right there, hard limit right there, hard limit right here, and these are the windows, and you have your four regions well segmented. Yeah, this is easy, and then you can use watershed and other methods. But how do you do it if your histogram is this way? Well, one way of doing that is let me switch the color. One way of doing that is k-means. You know, you can try to separate this into four clusters, but Gaussian mixture model actually assumes Gaussians, you know, that this entire histogram, this entire region is made up of a whole bunch of Gaussians. Let's say there is one right here, maybe one right here, and another one right here. So if you look at this, all I'm trying to do is mention that this histogram in blue is nothing but a combination of four individual Gaussians that are mixed at different ratios. This Gaussian has a specific width. This Gaussian is centered at some point, and this Gaussian has a specific height. Same with this. This Gaussian has some width and then centered at around some location, and then it has some height, right? So by mixing these four Gaussians, and each Gaussian having its own center, its own variance or standard deviation, yeah, and its own height, which is in a way you can think of that as the weight, you know, of this Gaussian. So if you have these four and mix it, this is the presumption of Gaussian mixture model. It is a probabilistic model that assumes that your data here is made up of a combination of individual Gaussians, okay, with unknown parameters. What parameters? You know, I just mentioned these three parameters. Okay, think of this as k-means, except we introduce this variance term. Okay, so if you remember, in k-means we are doing hard assignments, right? I mean, if you have a cluster right here, we are basically saying that, okay, if it is C1 center is right here, C2 center is right here, this point corresponds to C2. That's it, because it's closer to C2. This one corresponds to C2, and this one corresponds to C1. These are hard assignments of each data point. But think of that as this point is close to C1, but that is 98% C1 and only 2% C2. Okay, this is the primary difference if you want to draw analogy, you know, with k-means. This is the primary difference between Gaussian mixture model and the k-means. Okay, I'm spending this time so you understand exactly what the difference is here. Okay, so now how does this algorithm actually works? And actually, I'm actually assuming all of you know Gaussian. If not, again, let me take 30 seconds to 1 minute to quickly explain what a Gaussian is. Again, let me clear the screen so we have some room to talk about this. So a Gaussian is uh, nothing but a bell curve. If you probably called something a bell curve in the past, this is nothing but a Gaussian. So for example, I'm drawing a distribution right here, a bell curve. It has a center, okay? And it has standard deviation, let's say, which kind of defines how wide, you know, the bell curve is. And I mean, center is nothing but the mean. Okay, so mean is typically represented by mu right there. So if you want to write a mathematical equation for this one, okay, n as a function of your mu and sigma squared. I promise not to write any equations, but for those of you who love this stuff, this is for you. So a Gaussian is nothing but 1 over square root of whatever that value is, and then x minus mu, which is the center, whole squared over 2 sigma squared. Okay, the sigma is the standard deviation. Sigma squared is called variance. Okay, so we use variance because variance is what we use in the equation. Okay, so that's why instead of standard deviation, we typically use variance when we describe these Gaussians. So that's it. So Gaussian mixture model is nothing but take a bunch of these histograms, a bunch of these Gaussians, and mix them at a specific ratio, and then combine them to define the original data. Okay, and why Gaussian? Why not something else? Well, many data sets are Gaussian. That's as simple as it. Many data sets follow a normal distribution, which is represented by a Gaussian. That's why it's Gaussian mixture model. Okay, now this is a 1D example, but it can be in any dimensions. Okay, so for multivariate Gaussian, okay, if it's not just 1D, for multivariate Gaussian, instead of variance, we use something called covariance, okay, which is a matrix. And again, I do not want to get into the math for multiple reasons, primarily because I need to educate myself before I can talk about covariance to you guys. I know what it does and a little bit, but I'm not an expert. Okay, so let me stay out of it. This is out of the scope of this for this tutorial. So covariance, and why am I mentioning this? Because covariance is one of the inputs of our Gaussian mixture model. And again, implementation is very easy. I'm just giving you some background information. That's pretty much it. Okay, so now let's actually understand the Gaussian mixture model by taking one dimension example, okay, with some test data, not even test data, some data that I'm going to just draw on the screen right now. Okay, let me start by erasing the screen as usual. So let's say we have again one-dimensional data, okay, which is true with our image processing, right? I mean, with our image processing, even though it's a two-dimensional data, we are flattening it, or we are going to reshape that two-dimension into almost like a one-dimensional data. So along one dimension, let's just look at some data points. Okay, I have a data point here, I have a data point there, and so on. So I have a few of these data points, and we need to segment them into, let's say, two different regions. Okay, so we need to segment them into two different regions. So how do we do that? Let me say, let's say we have one region that's blue. So I'm going to draw a Gaussian right here, and then I'm going to draw another Gaussian. Since I already used red, let's actually use green. Okay, so another Gaussian, maybe the Gaussians overlap right here. Okay, so these are the two Gaussians that I'm using. My n equals to 2 in this case, or my number of clusters that I'm trying to create here is 2, or number of regions I'm trying to separate is 2. So now what it does is, in k-means, it's actually a hard assignment, right? So which data point does this, which Gaussian does this, generates this data point, for example. So in this case, it's not a hard assignment. It's like I mentioned earlier, this one is closer to the green, center of the green right here. The center of the blue is right there. This one's closer to the center of the green. So this will be, let's say, 98% green, and then blue would be, I don't know, 2%, right? I mean, the remaining 2% would be blue. So we are 98% confident that this data point is generated by green curve, and 2% confident that it's generated by the blue curve. So every data point has some probability, and as you can imagine, when you come to the blue side, this data point is probably, let's say, 80% blue, and then for green, it's the remaining 20% here. Okay, so for that data point, so this one. So for each data point, it's going to, we calculate the probability. I'm just saying, like 98%, I mean, it's the probability that this data point was generated by a Gaussian. And it does that for all of the Gaussians. If we have 5 different, then it does that for all of those 5. Again, this is not a hard assignment. In k-means, it's a hard assignment. Either this belongs to green or it belongs to blue. Okay. Now, what happens is, okay, once it's assigned, then it takes in, instead of actually, remember in k-means, it's moving the average or the center, to the average of all the data points. Very similar here. It updates the mean, the variance, and the weight. Okay, it updates that. And how does it update it? It's actually takes the average of all, just like k-means, except each data point is weighted by its probability. Okay, so instead of actually calculating an average just like in k-means, it actually weights it based on its probability. That is the only difference. And by the way, what I just explained is called expectation maximization. Expectation, okay, and Gaussian mixture models uses this, and expectation maximization. Please go ahead and read about it if you're curious. Expectation step is basically calculating the probabilities. Okay, this is the expectation step. Calculates the probabilities for each data point, and maximization step is nothing but updating the mean, the variance, and the weight each time. So for example, the second iteration of this could actually look like, well, or maybe the first iteration, if you want to call this, the first iteration of this could look like, okay, so now you have your blue right here. So the blue may be expanded a little bit, and green, because this one is very close, very much close to green, right? So this one is closer to green. We have a lot more data points that we think fall under green. So for the next step, the green would go all the way from right there. Okay, so this is the new mean for green, and this is the new variance for green. And in the next iteration, it does exactly the same calculation, right? So it does again the probabilities, updates the probabilities, and then it updates the mean, variance, and weights by averaging all points weighted by their respective probabilities. So I'm not sure if I confused you more or if I helped you in understanding this, but this is the background of Gaussian mixture model. If you think my explanation is not good enough, go ahead and Google search. There are a lot of videos, and we all learn in different ways. So find one that really explains you what Gaussian mixture model is. But let's actually write the code. For Gaussian mixture model, which again is very straightforward and simple, and let's try to segment an image. So for test images, I downloaded a couple of images by just doing some Google search. And let me just bring up a couple of these images so we can see. So image one is an RGB, a color image of what appears to be plant cells. And another image that I've used in the past, this is the backscattered electron image of a granite, a rock sample. And another one is a binary, appears to be some sort of an alloy here. So these are the three, and there is some noise, artificial noise, I guess, added to this specific image. So let's see if we can segment these images. And this is binary, that's probably binary. And this one, I don't know how many phases, 1, 2, 3, 4. But let's actually start with the plant cells, okay? And let me fire up our spider interface, and let me go ahead and zoom in so you can see this better. Also on the right hand side a little bit in the console. Okay, there you go. So now let's start with step one, which is always, I always import some libraries whether I need it or not. We'll figure it out as we go along. So numpy as np. Okay, and of course import cv2 so we can import our images. I'm also going to import another library from scikit-learn later on, but let's just do this step by step. Okay, so read the image as step one. We know how to do that, cv2.imread. And we said we want to use the life science, I mean the plant cells, so it's just plant underscore cells.jpg. Plant underscore cells.jpg. Okay, now that we have an image, again, let me go ahead and run it so we know it's reading fine. It's 1125 by 1500 by 3. 3 represents to the 3 RGB channels that we have. Now, the first thing that we need, whether it is k-means or any of this, these type of algorithms, again, flatten this or reshape this, I should say, not flatten. I'm just assigning another variable called image2. This is nothing but image1 reshaped into minus, oh, where is it? -1 and 3. This is nothing but reshape this into -1 is a shortcut of basically saying 1125 by 1500. Multiply these. 1125 times 1500 and 3. Okay, that's what this -1 is. I could have just taken these numbers and multiplied that. So that's pretty much the same thing. Now that we have our input data, let's go ahead. In fact, let's go ahead and run this so you can actually see what I mean. So image 2 is nothing but 1687500 by 3. Okay, still the same. You can see 218, 175, 34. So we're not changing any data there. Okay, so from sklearn dot mixture. Okay, this is where we have our Gaussian mixture. I'm going to import Gaussian mixture mixture. Let's import that as GMM so we don't have to type the full long name Gaussian mixture. Let me go ahead and run this to make sure I typed everything okay. That looks good. Now, let's define the model. Okay, so every time, again, the 3 steps when we do k-means or again Gaussian mixture or any of these most of these machine learning models. One, you define the instance, yeah, you define the model, and number 2, you fit it to the data that you have, and number 3, you predict it on the data. Okay, so step number 1, and in fact I'm going to mix step number 1 and 2. I'm going to do GMM model is nothing but our GMM. Okay, and if you look here, number of components is how many components do we want to divide our data into, or how many clusters basically. Okay, and then look at the covariance type. Okay, I'm just going to stick with these two for now, parameters. And you can look at the documentation if you want to use others, but number of components, because this is plant, I think we have 2. Let's start with 2. Okay, and covariance type, uh, let me use something called tide. Okay, again, if you look at the documentation of this on scikit-learn, it explains a bit more. The 4 options that we have choices for covariance are by default it's full. Okay, tide is another one. Diagonal is another option, and spherical. For example, if you choose spherical, I believe it actually constrains the clusters to spherical, regions basically. Again, and if you use diagonal, I think it includes actually full probably includes these ellipse type of definition of these clusters. Again, go ahead and read it out. I normally just use all 4 and see, okay, which one works very well, because I cannot tell you that tide works well for these type of samples or full works for a different type. Completely depends on the type of data and what you're trying to extract out of the data. So that's why I'm not spending too much time, or at least I didn't care to understand too much about what these individual covariance types are. So now that I have this, what else do I need? Well, let's go ahead and fit it in the same step, okay, to our image 2, right? I mean, that's what we are using right there. So again, all I'm doing in this step is creating a model and invoking my GMM, right? Gaussian mixture that we just defined here. And then as parameters, I want to divide this data into 2 components with a covariance type of tide. And now I just need to generate my labels. That's it. It's very simple. So labels, again, we just created the instance called GMM model dot predict. Okay, predict on what? Predict on my image 2. That's it. So it's done. I mean, if I run this, hopefully it should work, and it may take some time because that's tremendous amount. I mean, that's a lot of data. It'll take a while. As long as I don't get any errors, I'm done right now. But we need to put these numbers back. You see that seems to work well, and labels are created. Now, okay, they're created. How do I visualize them? Let's put the numbers back into original shape. Okay, meaning we need to reconstruct the image into our original shape. So first of all, let's understand what our original shape is. I'm just going to create a variable called original shape, and which is nothing but image.shape. Okay, so my original image is img, so I'm just going to create there are many ways of getting back to original shape. This is one way that I chose to do. uh, so now what? So let's take our GMM labels and reshape them into our original shape. Okay, but my original shape is m by n by the number of channels, right? So 1125 by 1500 by 3. Right now, the segmented image is only one. It's not an RGB image. So I just need 1125 and 1500. So my original shape 0, which is nothing but 1125, and then my original shape 1, right? What is 1 here? Again, in this array, my 1 is 1500. Okay, so all I'm doing is you can actually, instead of typing all of this and then defining this, if you know your original shape, just type 1125 comma 1500. That also works okay. Okay, so that's it. So now I can go ahead and cv2 im write, what shall we call this, segmented plant dot jpeg. Okay, that's pretty much it. Let's go ahead and run it, and once it's done, we should see. Let me go ahead and open the image as soon as it's done. Okay, so obviously I made a mistake right here. I just did segmented plant.jpg, but I didn't tell what to do. Write segmented as segmented.jpg. Let's do this one more time. There you go. Here is my image, and I'm not seeing anything. That's because the image labels are 0 and 1. That's it. Okay, so let me change my range in this image. Again, if you're curious, I'm actually using ImageJ program to open the image, and let me go ahead and adjust my brightness and contrast, and let me set it, instead of 0 to 255, let's just do 0 to 2. Okay, there you go. Isn't that great? Let's open this original image so you can see. There it is. So here is the original image. Here is the segmented image with n equals to 2. So it seems to do a decent job for the most part. I'm looking at this region. What's going on there? Well, if you look here, it's ambiguous right there. Okay, but in general, even with this split right here, it's actually doing a pretty good job. So this is how you do your Gaussian mixture model. Let's work on this other image. Which one? BSC image right there. Okay. How many regions would you say? Maybe 1, 2, 3, and 4. It could be 5. Let's just say 4. By the way, let me record another video after this one to talk about how do you pick how many number of clusters to segment an image into. If you know the application, you should know that, okay, I should have 4 of these or 3 of these. But if you don't know it, if you're ambiguous, there is a way to find out what is the optimal number of Gaussians, and I'll save that for the next video. This one is already long enough anyway. So just to finish this off, let's just do this on our BSC image, and let's say number of components for run it. There you go. Well, it's going to say segmented plant. I didn't change it, but that's okay. Let's go ahead and open that image and see how it looks like. Again, we started off with we got a dark image, but let me go ahead and adjust the brightness and contrast. 0 instead of 255, let's now go to 0 to 4 because we have 4 of these, and there you go. So region 1, 2, 3, and 4. So there the value is 2, here the value is 1, 0, and so on. Okay, here is how you segment your images using Gaussian mixture model. The code itself is very easy, but it always helps to understand the story behind it, the theory behind it, so you can optimize this. So now I'll leave it to you to change this tide into diagonal or something else. So I hope you liked this tutorial. I hope you found this to be informative and useful. If so, please go ahead and like this video on YouTube and subscribe to my channel. Thank you very much.